Hi everyone. So this is the last topic of M1. Congratulations for getting this far. Now, this is on moments. So what is moments? What is the moment of a force? What does that mean? Well, the moment of the force is defined by tau. That's that funny T there. So that's called tau, which is like that. You may know that as being 2 pi, the number 2 pi. Um, watch number file and then you'll know about it. So tau equals force times perpendicular distance. So this is force and this is perpendicular distance from the force to the pivot. Okay? So what does that mean really? It means turning effect. So you may know this from your GCSE, but the moment describes the turning effect. So if you imagine this situation here, this is a bird's eye view of a door, let's say. So this dotted line is a door. Okay, bird's eye view of the door, someone pushing the door, and this thing then will turn, won't it? It will turn round this hinge point, its pivot point. Okay, so the moment of the force is going to be FD. Now, what unit is that? Well, F, the force, is obviously in newtons, and distance is in meters, so this is Newton meters. And for people who know physics and stuff, you also know that as joules, but we'll do it in Newton meters for a moment's problem. Okay? So, we could go straight into the M1 side of things, but I think it's really important setting you up for M2 to make sure you really understand what moments are and how you calculate them. And that perpendicular distance means everything, that D here, okay? So can you see for diagram 2, if we wanted to describe the moments happening, tau would equal that force F, which we can see. You can see the force F, but the problem is we don't have a D because D is not perpendicular to the force. Can you see D is actually here? It is not this distance, it's this one, perpendicular to the force. So we need to know what that D is, and the only way we're going to know that is through using theta, that element of theta. So if we know the length of this door, so again, if we use it as a door, let's call that x. So the length of the door of x, we know that sine theta from the drawing, sine theta is opposite the angle over the hypotenuse, which is x, and therefore d must be x sine theta. Can you see? So FD is actually fx sine theta Newton meters, and which way is it going to turn? It's going to turn clockwise, so you can put clockwise there, right? So I'm not teaching you for this first year, I'm teaching you for the second year as well, setting you up for that second year, okay? The problems in M1 are not going to be like this at the moment, but it's worth you understanding where stuff comes from. So let's look at number 3. So number 3, what we're talking about here is what's called the sum of moments, okay? So the sum of moments means, well, if someone's pushing anti-clockwise and another person's pushing clockwise, who wins? Which way does it actually turn, and by how much of a turning effect is it? So what you need to do is you need to calculate the clockwise moments. So if we clockwise moments, right? And the way to lay this out properly, though, is to say moments around P clockwise. Do you see? MP clockwise. So we're talking about this 5 Newton force here, right? So here, tau clockwise is force is 5, so always the same, FD, and D is 2, that is the perpendicular distance, so this is 10, yeah? Whereas if we take moments around P anti-clockwise, so tau of ACW, what way is that going? Well, our force is 8, we can see the force 8 here, but we need a perpendicular distance to the force, remember, d. We have a hypotenuse, so let's just quickly see. We know that sine 50 degrees then is d over hypotenuse, so therefore d is hypotenuse sine 50, which is, write that in my calculator, make sure my calculator is in degrees, 8 times 2 times sine 50, so that's 12.257 Newton meters. So therefore, sum of moments, or SOM, is going to be anti-clockwise, take away the clockwise, so 12.257 minus 10 is 2.257 Newton meters, and it's going to turn anti-clockwise. Do you see? And there's your answer. A little bit more on that then, just a couple more. This is more similar to what you're going to be doing in M1. If you imagine that this is a beam, and we're going to talk about this in a minute, this is the beam here, and you've got a force applied here, force applied here, and a force applied here, and this is the pivot point, this is the hinge. So if you imagine this is a massive door, actually, let's say a door instead of a beam, a bird's eye view of a door, all these people pushing at the door, you've got someone pushing here, so someone pushing there, someone pushing there, etc. Okay, pushing the door, which way is it going to turn and by how much? So that was 1 meter there. Just get rid of that. Cool. So let's do the same again. So we've got moments around P, and we want to do clockwise first, let's say. So which ones are going to go clockwise? Well, imagine it. If this person's pushing, this is going to take us round. So let's deal with that first. So tau clockwise is going to be 5 times by the distance, the perpendicular distance. This is at right angles to the pivot point. So this is 3 meters. Any other ones going clockwise? No, there aren't. So this is 15. Yeah? Moments around P anti-clockwise now. So tau anti-clockwise. This time we've got 4 newtons here. So 4. Perpendicular distance is 1. Plus this one as well. There's 3 newtons and the perpendicular distance is 1. So this is 7 newtons. So 7 Newton meters, sorry. So therefore, SOM is going to be clockwise, so largest takes smallest. So 15 minus 7, so therefore 8 Newton meters, and the whole thing is going to turn clockwise in the end. Okay? So just a brief exercise to introduce moments and how to calculate them before we move on to the proper M1 stuff. Again, though, we've got, let's imagine this is a door, someone's pushing and pulling them at angles. What's the sum of the moments of the force going to be? Well, let's go for it. So moments around P, there's our pivot. Let's do the anti-clockwise first. So tau anti-clockwise. This one, if we continue this round, it's going to spin round, isn't it? So let's do that. So force is 4, and now perpendicular distance from the force to the pivot, right? Force to the pivot. So if this is D, therefore sine 35 equals opposite over hypotenuse, so hypotenuse sine 35, which is 32 sine 35, 18.35. And tau clockwise then, moments about P clockwise. This one we've got 7 newtons, and this is spinning around this way then, and there's our D then. And hopefully we're getting the hang of this. It's just going to be hypotenuse sine 25, because our angle is opposite the distance that we want. So that's 7 times 8 times sine 25. So that's 23.67. Therefore, sum of moments, clockwise subtract anti-clockwise, 23.67 subtract 18.35 equals 5.32 Newton meters, and the whole thing is going to spin clockwise. Fantastic. Last one. Do we need to do this? Fine. Extend the force. There's our distance d. So moments around p. Whoops. Moments around p. This time we're going anti-clockwise, aren't we? So tau anti-clockwise, or sum of moments, is force 5, and now we need this distance d, and it's going to be the same. The d is opposite the angle, and therefore hypotenuse sine 25. Done. Okay, cool. That's just general moments then, and now we're going into the M1 work, and we're going to apply them. So compared to that, this is relatively simple. So what we have is this idea of, yep, I know we're probably laughing at this, uniform rigid rods. What does uniform mean? Uniform means that your mass is evenly distributed across the whole object, across the whole rod. So rigid means that it doesn't flex, and a rod just means it has one particle thickness. Okay, so this rod in front of us here is just made of an infinite number of particles lined up together. Now, when a rigid rod is in equilibrium, the sum of moments about any point, and this is really important, any point will be zero, i.e. anti-clockwise moments will equal clockwise moments all the time. So anti-clockwise will always equal clockwise if a rigid body is in equilibrium. And that makes sense, doesn't it? It doesn't matter if something's in equilibrium, if you put a hinge somewhere, anywhere, it's not going to change, is it? Because it's still, everything's balanced out. It's not going to move anywhere. Okay? In other words, if this rod here is in equilibrium, me adding another stabilizer there isn't going to make any difference. Okay. Well, actually, no, it would. What I mean by that is, if I took moments from here, the anti-clockwise and clockwise would be the same. If I took moments from here, the anti-clockwise and clockwise would be the same. It would change if I put another. It would change if I put another stabilizer in there because the normal reactions would change. So ignore what I just said. Cancel that one out. I'm not making this video again for that. All right. So what I'm saying is you can take the moments anywhere and they will be the same, anti-clockwise and clockwise. So as we've got a uniform rod, that means, like I say, all of the mass is evenly distributed, and therefore the center of mass is always going to be in the middle. So the center of mass of this rod is always going to be in the middle. So it's going to have a weight in the middle. So I've been given this 2 meters and 1 meter length. As we know that this is a uniform rod of length 3 meters and weight 20 newtons, there's 20 newtons then, not 20 G because it says a weight. Resting, so that means it's in equilibrium, horizontally on supports A and C, therefore it's touching A and it's touching C. So immediately we should be putting normal reactions here. And they're different reactions, so don't call them R, that doesn't make sense. Calculate the magnitude of the reaction at each of the supports. Now, we know this whole length is 2 up to A and C, but that doesn't really help us. My advice to you is to split up the lengths you know. So if I know the center of mass is halfway, then actually my ratios look like that. Now, how do I find the reaction at A and the reaction at C? This is where moments comes in. It's always the same technique, folks, okay? You could take moments at 2 points. At which point does it make sense to take it at? It makes sense to take moments, because remember, you can take moments anywhere. That P pivot point that we started with can move anywhere. It makes sense to take it at the pivots. Why? At the support, sorry. Why? Because remember, tau is force times distance. If you have a hinge at a door, let's say this is the door, yeah? This is the hinge, here's the door, and you start pushing or pulling the hinge, how much is that door going to move? Turn. It's not going to turn at all, is it? Because the perpendicular distance is 0 from the pivot point. If you just pull at the hinge, nothing's going to happen. and it's just super strong and it rips off, right? So it makes sense to me to take moments at the support points because that will eliminate RA or RC, won't it? Because the distance will be 0. But always the same. Step 1, resolve vertically. It makes life a lot easier. Resolve vertically. You've got 1, 2, 3 forces here. So if we resolve up and down, you can see that RA plus RC minus 20 must be 0. So you know that RA is 20 minus RC. Always resolve vertically first. And then you only need to take moments once. Okay? Now I'm going to take moments. So if I take moments at A, remember it makes sense to take it here, and let's just really illustrate why. And remember the sum of moments will be 0. So therefore, anti-clockwise will equal clockwise. So let's do the anti-clockwise first. So anti-clockwise moments, A to C, our force is RC, our distance is 2, which equals, and now let's do our clockwise, our force is 20, our distance is 1.5, and therefore RC must be 20 times 1.5 divided by 2, so 15 newtons. And as we know RC, we now know RA. RA must be 20 minus 15, 5 newtons. Okay? Next. So again, uniform rod, a uniform beam, so we've got to draw it from this information now, of mass 40 kilos, so, and length 5 meters, rests horizontally and supports C and D, where AC, so AC, there's A, there's C, is 1 meter, and DB, so we know B is the end, so that must be D, so that's 1 meter. Okay, and it's a uniform beam, so like I say, let's split this up. We know, and it's 40G, and a uniform beam means it's halfway, so split your distances up so it makes taking moments really easy. So the support is at C, so let's draw a support and a support at D, therefore there's a normal reaction, and therefore there's a normal reaction. Looking good. When a man of mass 80 kg stands on the beam at E, the magnitude of the reaction at D is twice the magnitude of the reaction at C. Find the distance AE. So, I don't know where E is. I don't know where the man's standing, but as the normal reaction of D is twice the reaction at C, I can only guess it's got to be somewhere around here, right? Because, well, I don't know where it is, but if that person stands there, will that make the whole thing tip? Will that make RC, will it all tip around this point RD? I don't know. I don't know if it's enough to make that happen. But let's guess then. So I'm going to guess that this is E, and this is where the man's standing. So this is the distance A to E. Okay, and that's what I'm trying to find. Now, remember it says here that the magnitude at D is twice the magnitude at C. So this is the same as 2RC. That's helpful. So always the same. Resolve vertically. So I've got RC plus 2RC is 80G plus 40G. So therefore RC is 120G over 3. So 40G. Helpful. Now we need to find the moments. Well, now we need to find that distance AE. And how do we find that? Well, we've got to use moments, haven't we? As I don't know the distance of AE, it's so much cleverer to take the distance from a point that you do know. And as I'm trying to find AE, I might as well take it from A, because then it will give me the distance AE, do you see? So moments around AE, it's in equilibrium, and therefore the sum of the moments anticlockwise equals the clockwise. So let's do the anticlockwise first. So force, RC, that's this one, times by the distance 1. Plus, this one's anticlockwise as well, isn't it? RD times by that distance, 1 plus 3, so 4. Equals now our clockwise, sorry. So 40g is our force, and that's times by 2.5 plus now 80g, and this is times our distance AE, which is the very thing we're trying to find. We know that RC is 40g. We know that RD is 2 lots of that, so that's 80g, all times 4 equals 40g, 2.5, 80g, AE. So if you rearrange to make AE the subject, we should get, so what we got, 40 times 9.8, plus you do this too, 80 times 9.8 times 4, minus 40 times 9.8 times 2.5, divided by 80 times 9.8. So I've got 13 over 4 meters. So that's 3.25 meters. So yeah, roughly where we guessed. Great. Last one then. Last one. This time I've got a non-uniform rigid rod. Therefore, as it's non-uniform, I do not know where the center of mass is because it's not evenly distributed. Imagine a plank of wood that you've just cut up or something. They're going to get thicker end maybe, and a narrow end at one end. It's not going to be evenly distributed. Okay, so rod AB is 3 meters long and has weight 20, so that's all right. It is in a horizontal position, resting, so that means equilibrium on support C and D, where AC is 1. So there's C, normal reaction instantly, 1. And AD is 2.5. So D, RD, and that's 1.5 along, isn't it, from A. The magnitude of the reaction at C is 3 times the magnitude at D. So therefore RC is 3 RD. We know that much. See, we're just slotting in the information. Find the distance center of mass from A. So again, don't know where the center of mass is. Don't know. Maybe it's closer to RC. I'll let the maths tell me what it is. So the weight is 20, and here let's call that distance D. So find the distance of the center of mass D. Let's go. So resolve up and down again. So we get 3RD plus RD is 20. Therefore RD is 5. Take moments again at one end, moments at A, and let's do it. So anti-clockwise. So we've got 3 lots of RD. There's a force times by 1 plus RD 2.5 must equal our force 20 and then our distance D. And therefore D will equal, because we know that RD is 5, so we got 3 times 5 plus 5 times 2.5 divided by 20. So I've got 11 over 8, so 1.375. But where's 1.375? It's about there. Okay, so I was off there. So there we go. That's essentially moments, but they do get a lot trickier than this. This is just the basic theory.